Hi all, so today we're going to be going over the group work from March 1st. This is on chapter 15. And if you remember, I'll say I'm not going to work on the first one because we went over that argumentation in class, so I'm just going to start here on this page, the second page. And if you remember back in the beginning of OCHEM when we talked about molecular orbital theory, usually lone pairs were considered to go into an orbital. So like normally you would learn that if you had this atom, like an oxygen or a sulfur, that would be a sp3 hybridized. Those lone pairs would go into the hybrid orbitals. And that's because at that time, hybrid orbitals were the most stable thing you knew about. But I'm going to ask you to expand your horizon. And now I want you to think about the fact that p orbitals in resonance in an aromatic ring are actually more stable than just an sp3 hybridized orbital, right? Like if we can have aromaticity, that's better, that's more stable. So actually now you can learn that lone pairs will go into a p orbital as long as it's, the same on the same axis. So we'll say this is the y-axis. It will go into the y-axis p orbital if there's one available and if that will make the ring more stable. So what I always do when I'm drawing, so I'm going to cover up this diagram. I'll draw this diagram for you. Let's say it's an oxygen. I'll start by drawing the ring, and I don't worry about making it look too side to side because I'm just not really good at 3D structures, but I make sure all my orbitals look the same. So it's clear that they're going in the same direction. And I draw all my p orbitals. And then I'll go and fill in where there's a double bond. So right here, there's a double bond that's made up of 2 electrons. So there's one in each of these p orbitals, and that's kind of overlapping. And then the same thing over here on this side. So you can see all of these p orbitals are overlapping, and they all have 1 electron at least in them. So you have an unbroken ring of p orbitals on this side. But now we have this oxygen with 2 lone pairs, and we're asking ourselves, what do we do with that? Well, after you've filled in the double bonds and you've filled in your electrons for your double bonds, you need to ask yourself 2 things. Is there an empty p orbital? Sorry if you can hear any noise. My husband's in the background making lunch. Is there an empty p orbital? If there is an empty p orbital, then the next question you have to ask yourself is, will it help get to the right number of electrons? So 4n plus 2 pi electrons. So if it'll do that, if it has an empty p orbital and it'll help get to the 2 pi electrons, then it'll go into the p orbital, but if not, it'll go into a hybrid orbital. So in this case, you have 2 lone pairs, and you do have an empty p orbital. It's not taken up by a double bond. So one will go, then you have to ask, will it do 4n plus 2 pi? Well, there's 4 electrons here, so adding 2 more is 4n plus 2, total of 6. So one of your lone pairs will go in that p orbital. Now there is another p orbital that's like perpendicular to this one. That doesn't matter as much as, that's not as stable as much as a hybrid orbital. So the other one will go off to the side in your hybrid sp2 orbital. So it's basically a flat triangle made here, here, and here. Those are your hybrid sp2 orbitals. So I'll draw, this is an sp2, this is an sp2, and this is an sp2. And then you have 1 lone pair in the p. So that's kind of how I approach these questions. Now, if you already had, let's do one like, if there was an option, I know which one would be good, like this, right here. So this has your 2 p orbitals. There's an electron in each one, and then you have to decide what to do here. Is there an empty p orbital? Yes, there's not a double bond right there, but will it contribute to the 4n plus 2 pi electrons? Well, technically, no. If this went into the p orbital, you'd have a total of 4 pi electrons. So instead, that would be anti-aromatic. So either this would be anti-aromatic, or it could go into the hybrid and be an sp3 hybrid orbital off to the side, and that would be non-aromatic. So that would probably be more stable. But if it was forced into the pi, it would be anti-aromatic. So that's kind of what you have to ask yourself. Is this going to help the ring? Is it going to make it more stable by putting this in the p orbital if there isn't even an empty p orbital? So in this case, one of your lone pairs goes into the p orbital for a total of 6 electrons, and the other is off to the side in a hybrid orbital. And this makes a flat triangle right here. Boom, boom, boom. That's like the, like in carbocations when it can attack from either the top or the bottom. Okay, now over here, let's do the same thing. I'm going to redraw it for you just so we get some practice. Actually, this one and this one are the same. So let's just draw it right down here. So here's my drawing out. I'm going to start with my double bonds. Here and here, here and here. So these are filled up with a double bond. Oh man, it was off screen. Okay, so these are each filled up with a double bond. But this one, we know there's a lone pair, but we don't know if it's in a p orbital or not. So our double bonds are taken up. Now let's decide on this lone pair right here. So the first question, is there an empty p orbital? Well, yeah, it's not taken up by a double bond, so it could go there. And then the second question, will it help the 4n plus 2 pi electrons? So there is an empty p for sure. Will it help 4n plus 2 pi electrons? Right now there's 4 electrons, so if you put 2 right here, that gets you to 6. So yes, that is in the empty p orbital. It will not go into a hybrid orbital. Okay, now this one down below is a little bit more complicated. I'm going to turn it to where the H is on top because that's easier for me to see. So this is what we have. There's a lone pair here and here on these nitrogens. So you have to know your Lewis structure rules to know about those lone pairs. But I'm going to start with my double bond here, here, and here. So there's a p orbital here and here and a p orbital here and here. So now let's start with this nitrogen. There is an extra lone pair on that nitrogen, but is there an empty p orbital for it to go into? Actually, no. That p orbital is already taken up by the double bond. So it's going to go off to the side into an sp2 hybrid orbital. Now so we couldn't even ask the second question. Now this one up top, this does have an empty p orbital. And so then the question is, would it help 4n plus 2 pi? So it has an empty p orbital on this one. And will it help 4n plus 2 pi? Well, there's only 1, 2, 3, 4 electrons total. So yes, it would make 8. Or it would make 6, sorry. So that would be an aromatic ring. And so with this. Actually, all these are aromatic. Okay, so the next one, we have, I'm going to draw it without the double bonds. We have our p orbitals for each of our double bonds. So we'll just start right here. Here's one double bond. Here's another double bond. And here's a third double bond. So that's all our double bonds. And then we have to decide on our lone pair. So there's a lone pair on that nitrogen. Nitrogen always has 3 bonds and a lone pair if it's neutral. So I'm looking at this nitrogen. There's not an empty p orbital, so it has to go into the sp2 hybrid orbital off to the side. It can't even think about going into the p orbital. If it did, it would force this one out, go up there, and be 7 electrons in the ring. So that just doesn't really make sense. Okay, so now the next question is, why does NMR spectra for benzene provide evidence for the delocalization of pi electrons? Well, really what it provides evidence for is that each one of these is in the exact same environment. So because there's only one peak, and it also says there's no neighbors. So like if you remember what we learned about NMR is it can split, right? Like according to n plus 1. So if you have ethanol, this hydrogen doesn't have any neighbors because of that oxygen, so it would appear as a single peak. This hydrogen right here, there's 2 hydrogens, it has 3 neighbors. So 3 neighbors plus 1, it would appear as a quartet. And these 3 have 2 neighbors, so it would appear as a triplet. This peak does not appear as if it has any neighbors at all, which means each of these is identically the same. So if all of these hydrogens are identically the same, that means that those electrons are perfectly delocalized around it and they're all experiencing the exact same environment. Okay, the next question is, I feel like I don't know if I could have said more on that. If you have some clarifying questions you want to ask or whatever, you can, but that's kind of just like, I don't know how much you could work through that as much as just thinking about the way NMRs work is how I was able to answer that question. Okay. So the next question is, which is more basic and why? So more basic is going to be like if it bonds to a proton, right? Or if it acts as a Lewis base, it will be an electron donor. So which one's willing to give up its electrons or accept a proton, right? So proton acceptor, electron donor, whichever one makes more sense to you. So I'm going to go back to our structures that we drew. So for pyridine, we decided that this lone pair was off to the side, and all these were part of the resonance. And then for pyrrole, we decided that for each of the double bonds, they had one here, but this lone pair had to also be a part of the this to make it aromatic, because there has to be 6, right? So it had to be in the p orbital. So if this that's off to the side and is not taking part in the resonance bonds to a hydrogen, that won't matter. But if this that is taking part bonds to a hydrogen, it will convert this to an sp3 hybrid because there's not a double bond there, meaning it will break the aromaticity and make this non-aromatic, right? Because this is sp3 hybridized if there's something else bonded to it. And those are the only electrons that can form a bond, so it will break aromaticity. So the pyridine is more willing to accept a proton, so this is more basic. Whereas this does not want to react because its 2 electrons are going to get lost. Its 2 electrons that contribute to resonance are going to get lost, and then resonance will be broken. Aromaticity will be broken. So that kind of gives an example of how like all the things kind of go together, like whether or not it's aromatic, where the electrons are, and then how it acts when it interacts with other molecules. Okay, so I did a general mechanism for electrophilic aromatic substitution on my TikTok. You can go check that out. And I broke it down into 3 steps, which were generate the electrophile. Did I spell that wrong? Is it pH or electrophile? Now, for some reason, I can't remember. Then the benzene attacks. And then the aromaticity is restored. So we did that in really general terms with E+, and then the there's the hydrogens all the way around here. But this lone pair attack, or this double bond attacks, and you end up with all these hydrogens are still in place. So is this one. But then there's a positive charge down here. And it is important to note that this is resonance. You can just draw like dots around to show that it's a resonance hybrid, but it will really come into play when we do substitution on different carbons. That looks like an H, but so there you go. That's the resonance structures of this. So benzene attacks, and you have all the resonance structures. And then your base, which usually was generated when your electrophile was formed. This is a plus charge there. Your base will come in and steal a hydrogen just like you've seen before. The double bond will go there and fill in like with an elimination reaction. And you'll now have your substitution complete and your aromaticity is restored. So the overall reaction for electrophilic aromatic substitution is a benzene trades out a hydrogen for an electrophile. So that's a general mechanism. But I want to draw a little bit more detailed mechanism. So I'm going to use a pink marker, and I'm going to say, what if we reacted, this is a purple marker, benzene with Br2 in the presence of FeBr3. This would be really similar if you used Cl2 in the presence of FeCl3 or also AlCl3. Any acid, any Lewis acid like that will work. So the first step is the electrophile is generated. So actually that happens because bromine is partially negative and partially positive. Well, I should say bromine has an equal share of electrons, but when things come near other molecules, they can have an induced dipole. And when bromine comes really near to this this carbon center that it's neutral, or this iron right here is neutral, but it's missing electrons. So this bromine will become more negative, and it will actually try to come in and fill in here. But bromine it's not going to be happy if it has that number of bonds to it. So actually this one will break, and it leaves behind a Br+. So you can draw the arrows with the bromine attacking and then this bond breaking, or you can draw it like as if they form a double, like a complex like this. I'll accept either one. But this one's really partially positive and this one's really partially negative, and then eventually that just breaks. So either one of those I'm fine with, but essentially this is what happens to get your Br+. And then step 2, so that's step 1. Step 2, benzene attacks. And your aromaticity is broken. You get a bromine. There's still a hydrogen there and here. I'm not going to draw them just for clarity's sake. And there is resonance with that carbocation is spread around through here. It's not a full circle like we draw in the middle of benzene because the aromaticity is broken, but it is distributed here. So if you draw those dotted lines or draw all the structures, I'll accept either one of those. And then then your final step will occur where your aromaticity is restored. So this hydrogen will be taken. This will come and fill in here. And when I say base, it's actually usually the FeBr4 minus, but you can just write base and we'll accept it. And then you get your overall product. Now this is going to be on your quiz. Dr. Corrales made it very clear this is going to be on your quiz. They are going to put a question like this. It will be either a bromination, a chlorination, or I think the only other one we covered in class was like a nitration. So be sure that you know how to generate that electrophile, and then these last 2 steps are the same. But if you get into the quiz and you're kind of freaking out, it's better to have something than nothing. So if you can't remember, even just drawing the basics, like the E+ is better than nothing. Okay, that intermediate is called an rhenium ion. And this is kind of a weird way to phrase this question, but what it means when it says true intermediate is like, does it actually stop or is it a transition state? So like SN2, no true intermediate, right? It's like it just had its transition state, immediate. But SN1, we have that carbocation, which is a true intermediate. And this is very similar. You can isolate a carbocation and keep it. It's not going to last for very long. It's very reactive, but you can do it. And so technically there is a true intermediate that's this rhenium ion. What catalyst is needed for halogenation of benzene? So you always need an acid catalyst, and it's usually a Lewis acid like FeBr3 or AlCl3 because it's going to make that halogen really want to react with it. It wants to fill in the absence of electrons here because it doesn't have a full octet, and that will cause the halogen to become really positive. And then because the halogen is positive, which halogens freaking hate being positive, then your benzene is going to be willing to break its aromaticity to react. And then for this last one, rank the reactivity of halogens. This is always the same. Usually, I mean, I guess not always, but very usually, your fluorines are going to be the most reactive because they can have such an induced dipole. And then Cl2, Br2, and I2, you don't really see these reactions too much. This one's really slow and this one's too fast, but these happen a lot. And they all have, once you have either a chlorination or a bromination, you can do similar chemistries on them, so it doesn't super matter which. Okay, sorry that I had to go through this so quickly. I just wanted to make sure you got it before your quiz tomorrow, so I hope that was helpful. And if you need to ask clarifying questions, please feel free to put them down below. Good luck studying.